Hi, my name is Manish Gupta, and in this video, I'm going to talk about Google Flan PaLM model, Flan T5 model, and Flan UPaLM model. So let's get started. This particular work is about understanding how instruction fine-tuning works along with the other dimensions, like how does instruction fine-tuning work at scale? Can instruction fine-tuning be made better with the chain of thought prompts and so on? Right. So let's basically start by understanding what are some popular instruction fine-tuning data sets. So in the past 1 or 2 years, there has been a tremendous increase in the number of publicly available prompting data sets for instruction fine-tuning, starting from unified QA to CrossFit to natural instructions V1.0, Flan 2021, P3 dataset, Meta ICL dataset, and so on. So as you can see, these dataset collections, these fine-tuning instruction fine-tuning collections have been used to train various kinds of models, starting from unified QA to T0 kind of models, to Flan Lambda kind of models, TK instruct model, GPT-3 model with the self-instruct dataset, and then OPT IML models, and then in this current work that I'm going to talk about, they also introduced this new collection called as Flan 2022, which has been used to actually train Flan T5, Flan PaLM, and Flan UPaLM models. Um, the base models, of course, are different. So as you see, the base model for Flan T5 is going to be T5 itself. Flan PaLM, the base model is PaLM itself. And then for GPT-3 in self-instruct, for example, GPT-3 is the base model. Then for TK instruct, T5 LM and MT5 are the base models. For 3.0 model, again, T5 LM is the base model, and so on. Okay. The size of these models, of course, typically depend on the base model. So for example, for GPT-3, it is 175 billion, but for T5, they use they basically train a large number of models from 220 million checkpoints to 11 billion size checkpoints. Okay. Some of these are available publicly. The checkpoints are available publicly. So for example, of course, the GPT-3 self-instruct model is not publicly available, but then there is a T0 model, which is publicly available. There is also OPT IML models which are publicly available, and then there is Flan T5, which is publicly available, although Flan PaLM is not publicly available. Right. Now, the data collections, these collections essentially have either zero shot prompts, few shot prompts, zero shot or few shot prompts, or a combination of zero shot and few shot prompts. Right. There are several, these data sets differ also in terms of number of tasks. So the largest one so far had been supernatural instructions data set, a very large number of tasks. However, the Flan 2022 dataset also has large number of tasks, 1,836 different tasks in the collection. Right. OPT-IML bench, this particular dataset has 2,000 plus tasks in it. Right. Now, that's the number of tasks, but the datasets also differ in terms of number of examples. And this particular Flan 2022 collection actually has 15 million training examples, fine-tuning examples. The examples differ across other dimensions as well. For example, in Flan 2022, we have template variety, so different types of prompts. We also have input inversion, so not just the forward kind of prompts, but also you invert the task so as to form prompts for the inverted version as well, and multilinguality as well. So many of these existing data sets do not have all three of them, but then the Flan 2022 has all these three dimensions as well. So the Flan collection, the Flan 2022 collection scales to more instructive training tasks, 1,836 tasks. It combines training across three different types of prompts: zero shot prompts, few shot prompts, and chain of thought prompts. So zero shot prompting basically means just the instructions. Few shot prompts means instructions with some examples, and COT, the chain of thought prompts, basically mean that they have an explanation along with the answer, and that forms the instructions. So, and in this particular publication, when they used Flan 2022 collections is to train Flan T5 and Flan PaLM models, they basically showed that mixed prompting settings during training sort of improves prompting at inference time as well. Improves the performance at inference time across all kinds of prompting settings. So at inference time also, you could basically have few shot prompts or chain of thought prompts. And they have shown that, yes, if you basically train on a mixture of few shot, zero shot, and chain of thought prompts, then you get basically very good inference time results for few shot as well as chain of thought prompting settings as well, both on held in as well as held out kind of tasks. OK. So now let's talk about what are the Flan PaLM, Flan T5, and Flan UPaLM models. Well, at the outset, they are instruction fine-tuned models using the Flan 2022 collection that I talked about on the previous slide. So Flan PaLM has been instruction fine-tuned on the PaLM models, T5, Flan T5 on the T5 kind of models. As you can see, they actually fine-tuned models of different sizes. So Flan T5 models, for example, exist in 5 different sizes, and they follow an encoder-decoder architecture with span corruption as their pre-training objective. Flan PaLM models actually are decoder-only models, and there are 3 different sizes of those Flan PaLM models: 8 billion, 62 billion, 540 billion, but none of them are publicly available, right? Flan continued PaLM is yet another kind of a Flan PaLM model, and Flan UPaLM is again another kind of a Flan PaLM model, which are also decoder-only models. Now, that's about the base architecture. The way they have been fine-tuned is essentially using the Flan 2022 collection, but then they use a mixture of chain of thought prompting, few shot prompting, and zero shot prompting in the collection. So again, chain of thought prompting basically means trying to ask the model to answer the questions by reasoning step by step. So here is an example of instruction fine-tuning. So instruction fine-tuning means fine-tuning by giving instructions in a human format, right? So please answer the following question: what is the boiling point of nitrogen? And you expect the model to predict that. Chain of thought fine-tuning basically means you ask the model to answer the question by reasoning step by step. So you basically ask the question: the cafeteria had 23 apples. If they used 20 for lunch and bought 6 more, how many apples do they have? Now, the direct answer here would just be 9, but then a chain of thought prompting kind of a situation comes up with this kind of answer. The cafeteria had 23 apples originally. They used 20 to make lunch, so they had 23 minus 20 equal to 3. They bought 6 more apples, so therefore it is 6 plus 3, 3 plus 6, 9. Okay. So in this particular work, so as to train these kinds of models, what they've done is to actually multitask instruction fine-tune on 1800 plus tasks, and then infer on some unseen tasks. So, and then inference can also be in a chain of thought manner or a few shot manner or just zero shot manner also. Okay. Now they experiment with both with at least 2 dimensions. So, with chain of thought and without chain of thought. So you could basically, fine tune with chain of thought prompting or without chain of thought prompting. Also, you could basically fine tune with with exemplars or without exemplars. So zero shot or few shot. Okay. So here are examples of these kinds of things. So here is an example of without any example. There's no example. It's just the task instruction, and then you ask a question and you want an answer, right? On the other hand, this one also does not have any example, but this one essentially has chain of thought prompting setting prompt, right? So answer the question by reasoning step by step, and then you essentially expect a detailed answer step by step, not just the final answer, but also a chain of thought also in the answer. This is a setting without chain of thought, but it has few shot examples, specifically one shot. So where you basically have a question and you give an answer, and then you have another question and you expect the final answer from the model. This is basically a combination of few shot and chain of thought, where you have an example, a chain of thought example, step by step, and then you actually ask a question and expect it to answer by reasoning step by step. Okay. So as I mentioned, these models have been fine-tuned by using both few shot settings as well as chain of thought settings. So you have exemplars in the prompt as well as chain of thought kind of prompting as well. So how are these Flan models fine-tuned? Well, they have been fine-tuned using 473 datasets, 146 task categories, and 1,836 total tasks. Okay, so 1,836 total fine-tuning tasks actually are rather obtained from 4 different mixtures from prior work. These mixtures stand, they are Muffin, T0SF, NIV2, Natural Instructions V2, and COT reasoning tasks. As you can observe, these tasks are pretty diverse in nature. So Muffin tasks include natural language inferencing, question answering, program synthesis, code repair tasks, and so on. T0SF tasks include more of common sense reasoning, question generation, question answering, topic classification, and so on. Natural language instructions include a whole variety by itself. And then COT, the chain of thought reasoning, also includes various kinds of tasks like arithmetic reasoning, common sense reasoning, and so on. Okay. Now, they specifically held out 4 different tasks for evaluation. So MMLU, BBH, TidyQA, and MGSM. So we'll discuss more about these 4 later, but then as you can see, they also are pretty diverse in nature. They also include pretty diverse set of NLP processing tasks. So the interesting part about this fine-tuning of the Flan models is that they all use instruction fine-tuning, and instruction fine-tuning typically uses very small amount of compute. So therefore, fine-tuning compute is a small fraction relative to the training compute. If you compare it with the pre-training compute that is required, instruction fine-tuning typically takes much lesser amount of compute power. Just for a comparison, PaLM basically took about 512 V4 TPU chips for 37 hours, while fine-tuning Flan PaLM, 540 billion Flan PaLM from the PaLM model essentially takes 0.2% of this compute power. So it's pretty efficient in that sense. Now, how do the results look like? So how does instruction fine-tuning work with scale? So while doing instruction fine-tuning, you can care about 2 kinds of scaling. So one is about scaling the model size, and the other is about scaling the number of fine-tuning tasks. So as you can observe, these are results for Flan PaLM. So they basically scaled from 8 billion kind of checkpoints to 540 billion checkpoints, including the 62 billion checkpoint on the way as well. And what they observe, what you see here is, of course, on the y-axis, you see a sort of accuracy on held out tasks. And what you see here is, if you change the model size by varying the number of tasks as well, what do you observe? So you observe that if you don't do any fine tuning, even with the basic PaLM model, the accuracy improves as you increase the model size clearly, right? That's the gray curve. But scaling actually improves performance substantially for fine-tuned models as well. So essentially, as you see, with larger number of tasks, the fine-tuned model, of course, has better accuracy, but that accuracy also improves as you scale the model size. Okay. Now, what you see on the right side is basically on the x-axis, you see number of fine-tuning tasks. On the y-axis, you see the accuracy. And as you can see, of course, larger size models are expected to have higher accuracy. But what you also observe is that as you increase the number of tasks, the accuracy typically increases. The accuracy typically increases up to 282 tasks. After that, sort of the improvement is rather marginal, right? So here, the number of fine-tuning tasks were increased by adding tasks one by one from different task mixtures. So first 9 are from COT, then another next set is from Muffin, 80 tasks, and then from T0SF and NIV2, natural instructions V2. Yeah. So in short, with instruction fine-tuning scales up very nicely. So it shows improvements in the performance, both with the model size increase in terms of number of parameters, and also by increasing the number of fine-tuning tasks. So what is the impact of instruction fine-tuning with the chain of thought prompting and self-consistency? So chain of thought prompting is pretty popular. Essentially, you have to include in the prompt reasoning step by step, in which case the chain of, and you have to basically also train it with some examples which have detailed reasoning in the as part of the answer, and then the final answer, right? Now, self-consistency is basically an improvement over chain of thought prompting, where the decoding strategy is to replace the greedy decoding in chain of thought prompting by a more thought-through decoding strategy, self-consistency strategy. In self-consistency strategy, the idea is to sample a diverse set of reasoning paths instead of only taking the greedy one. Okay. So, and then the idea is to basically come up with the most consistent answer by marginalizing out the sampled reasoning paths. So the idea is as follows. So as to reach a final answer, you can actually take several paths, but then you can still reach the final correct unique answer. So therefore, the idea is why choose the most greedy path only, right? You could potentially choose multiple paths and still try to get to the same answer, thereby improving the overall learning, right? So self-consistency has been shown earlier to work really well with chain of thought prompting, and therefore they use self-consistency in this work as well. So what is observed with chain of thought prompting is that fine-tuning on chain of thought improves reasoning on held out tasks. Okay. So now the idea is, so let's look at this figure here. The results are shown on 5 different benchmark data sets. And what you observe is that results are shown for PaLM 540 billion model and Flan PaLM 540 billion model. Okay. Note that the PaLM 540 billion model is not instruction fine-tuned, right? So here at test time, when you essentially do direct prompting, you get some results. But if you do COT prompting, you typically observe better results. Only in a few cases. Well, yeah, COT prompting doesn't always help, but in general, COT prompting gives you better results. COT with self-consistency improves results everywhere. So everywhere you see COT with self-consistency improves results. And this is actually only at inference time, not instruction fine-tuning at all. Now, if you do instruction fine-tuning, so fine-tuning on COT sort of improves your reasoning on held out tasks significantly. So as you observe here, if you fine-tune on COT and then also do COT prompting, with self-consistency, the results that you obtain are really good. They are state of the art across many, many benchmarks that you see here. Yeah, of course, COT plus self-consistency along with instruction fine-tuning doesn't always give you the best results. I mean, there are some prior other models, state-of-the-art models for these two benchmark data sets which give best results, but then still it helps significantly. So on the very strong and difficult MMLU benchmark, it could actually move the accuracy to 75.2, while PaLM could only achieve 69.3 and Code DaVinci 002 could only achieve 68.3 and so on. Okay. So what is also observed is that if you basically evaluate on COT benchmarks and non-COT benchmarks, right? And if you essentially were not doing any fine tuning. So the gray line is when you don't do any fine tuning and you increase the model size, you obtain some accuracy, right? But then if you do COT plus non-COT fine tuning, in the sense that while fine tune time, instruction fine tune time, you basically fine tune with COT plus non-COT. That gives you better results on COT benchmarks. However, if you actually just fine tune on non-COT data sets, in fact, fine tuning hurts. So fine tuning is worse than no fine tuning. Okay. But the moment you actually add just a couple of those COT based tasks while fine tuning, your accuracy actually improves. The blue line is better than green line for sure, or gray line as well as the red line, which basically just uses COT only tasks for fine tuning. Okay. So another held out set, what we observe is that non-COT plus COT fine-tuning is better than COT alone, and clearly non-COT plus COT fine-tuning is better than no fine-tuning or non-COT fine-tuning. Okay. Now, what happens on held out non-COT benchmarks? On held out non-COT benchmarks, as you observe, non-COT only fine-tuning is of course better than no fine-tuning. Okay. However, non-COT plus COT fine-tuning is not worse. So what is the takeaway is basically that when you're doing instruction fine-tuning, your benchmark collection on which you do the fine-tuning should include some COT and some non-COT tasks as well. Okay. Now, lastly, fine-tuning Flan PaLM with some COT data included in the mixture actually enables zero-shot COT reasoning in unseen tasks. That's awesome. So these results basically show you. So let me go over the results. Right? They basically show you different model size of PaLM. Right? And the y-axis shows you BBH accuracy. So BBH is big bench hard tasks, which are really difficult tasks. Right? And what you observe is that a PaLM by itself, without instruction fine-tuning, but in a zero-shot manner, gives you some results. And then if you do zero shot plus COT prompting at prompt time, right? At prompt time, it's zero shot, so you don't do any few shot prompting, but you do COT prompting. You observe that PaLM model loses out on accuracy. Okay. At all scales, of course, with the scale increase, you get better results, but then doing COT prompting without fine tuning actually leads to poor results. But then if you do instruction fine-tuning, even the zero-shot accuracy is super awesome. But if you instruction fine-tune along with COT, your instruction fine-tune results are super awesome. So in short, the takeaway is that instruction fine-tuning with COT is a really good idea, along with, of course, the self-consistency based decoding. Okay. Now let me sort of talk about the real models, the models that this video that is the main focus of this video. So Flan PaLM, Flan T5, and Flan PaLM. Right. Now, as I mentioned earlier, they actually trained different model sizes. For example, Flan T5 has been trained 5 different model sizes. Flan PaLM, 4 different sizes, 4 different models in that senses, and then there is a UPaLM model. Okay. Now, the results are shown on 4 different benchmarks. So MMLU benchmark is about exam questions from 57 different tasks: maths, history, law, medicine, and so on. BBH is 23 challenging big bench hard tasks, for which PaLM basically performs below an average human rater. TidyQ is a question answering benchmark with 8 different diverse languages. MGSM is a multilingual benchmark of math word problems manually, which has been translated into 10 different languages. And what you observe is that, continued PaLM so what you observe is that there are results using the original model and then instruction fine-tuned model, Flan instruction fine-tuned model. Of course, this fine-tuning actually involves chain of thought prompting along with some zero shot, few shot chain of thought prompt kind of models, prompts in the collection, and also followed by self-consistency, right? So that's that. Now there are these two special models, continuous PaLM and UPaLM. They're variants of PaLM, which has been, they initialized from the PaLM model. So PaLM 62 billion model or PaLM 540 billion parameter model. And then they pre-train, for example, continued PaLM is pre-trained further on 500 billion tokens, while UPaLM model is further pre-trained for 20K additional steps using the UL2 objective. So which is the RxS denoising objective, R denoising, X denoising, and S denoising, 3 different kinds of denoising that they do. Okay. So what are the observations in terms of the overall results? So the results are shown when at inference time you actually directly use the instruction prompt, or you do chain of thought prompting, right? So of course you do chain of thought prompting at fine-tune time for everything, wherever you see Flan, right? But then at inference time, you could either directly when you do the inference, or you do chain of thought prompting based inference with self-consistency, right? So what you observe is that the best model here. So first observation is that yes, instruction fine-tuning helps everywhere, right? So everywhere, wherever you see, so this is the normalized average across all the tasks. What you observe is that you see so much of gain across different model sizes and different kinds of models based with respect to the non-instruction fine-tuned model. What you also observe is that this 3 billion Flan T5 XL model, when evaluated on the difficult MMLU benchmark, gives you 52.4%, right? Surpassing 43.9% even by a 175 billion parameter GPT-3 model. So remember, GPT-3 also is an instruction fine-tuned model. However, they have added their extra sauces of chain of thought prompting along with the fine-tuning benchmark collection is of course very different. So that's that. The best model in this entire table is essentially the Flan UPaLM model. And the nice part is that instruction fine-tuning, so what this shows is that instruction fine-tuning along with the UL2 continued pre-training actually are complementary. So you take the UPaLM model, which has been pre-trained already further using the UL2 objective, and on top of that, you instruction fine-tune using the Flan collection. And what you observe is that they're complementary. There is gain in between these two guys as well, which basically shows that the UL2 pre-training and instruction fine-tuning are really good ways of improving the accuracy, besides, of course, increasing the model scale. Okay, so let's talk about some examples, PaLM versus Flan PaLM. So here are some examples. This is a Boolean expressions task. The question is false or not false or false. What is it? So let's think step by step. So this is an example of chain of thought prompting. And what you observe is that PaLM 540 billion model just does not get it. But Flan PaLM 540 billion does get the right answer after explaining very nicely the reasoning process. Okay. Here is another example of disambiguation question answering. So there is in the following sentence, explain the antecedent of the pronoun or state that it is ambiguous. So the sentence is the reporter and the chef will discuss their favorite dishes. And if to choose one of the 3 options, they will discuss the reporter's favorite dishes, they'll discuss the chef's favorite dishes, or it's ambiguous. Yeah. Now, the PaLM 540 billion parameter model just does not get it. It basically gets into this repetitive mode. Reporter and chef will discuss their favorite dishes. Reporter and chef will discuss reporter's favorite dishes, and so on and so forth, right? So it does not answer the question, right? But Flan PaLM 540 billion very nicely gives the reasoning and also answers it correctly. So reporter and chef will discuss their favorite dishes does not indicate whose favorite dishes they will discuss, and so the answer is C. Okay. So overall, Flan PaLM model is better even qualitatively, as we can observe from these examples, compared to just the PaLM model. In fact, here is a very good win of the Flan PaLM model. So Flan PaLM models, introduced in October 2022, 5-shot prompting along with chain of thought prompting and self-consistency gives you 75.2 on the very hard MMLU task. Right? For this task, the random accuracy would be 25%, an average human reader accuracy is 34.5, and an average human expert accuracy is 89.8. So getting 75.2 on this is a big win for the Flan PaLM model. Okay, so let me quickly summarize this video. In this video, I talked about Flan PaLM, Flan T5, and Flan UPaLM models, which have been instruction fine-tuned using the Flan 2022 collection, right? This particular paper showed that scaling both model size and number of fine-tuning tasks improves performance. Scaling number of tasks has diminishing returns, but does increase the performance as the number of tasks are increased. Fine-tuning on non-chain of thought task degrades performance on chain of thought tasks only. However, jointly fine-tuning on both chain of thought prompting based tasks as well as non-chain of thought prompting based tasks actually helps. Instruction fine-tuning is general. It sort of works well with decoder only and encoder decoder models, as has been shown by instruction fine-tuning, the typical PaLM model, which is decoder only, and T5 model, which is encoder decoder model. Instruction fine-tuning combines really well with other model adaptation techniques such as UL2R, and that basically says that there is good hope of sort of improving the performance of these models without really resorting to increase the model size. Instruction fine-tuning is also relatively compute efficient. Plus, the smaller models oftentimes have been shown, smaller models which have been instruction fine-tuned oftentimes have been shown to outperform larger models without instruction fine-tuning. Overall, the Flan T5 checkpoints are publicly available for you to experiment. Flan PaLM and Flan UPaLM checkpoints, although, are not publicly available. Okay. So that's it for this video. Hope you enjoyed it. Thanks for watching. Connect with me on my LinkedIn or look at my research on my homepage.